Welcome to this video. This is topic 13 of Edexcel International A-Level Chemistry for Unit 4. This is the third topic of Unit 4. After that, we only have 2 topics left, hopefully finished by August, by the end of August or start of September. So I'll be taking a break. And this is also the topic 11 for Edexcel A-Level Chemistry. This equilibrium in second year or A2 builds upon knowledge learned from AS. For international candidates, in Unit 2 we had learned equilibrium 1, so this is basically equilibrium 2. But the people doing it in the UK, the A-level candidates, their equilibrium 1 already had some of the things learned that we learn in equilibrium 2, us international candidates. So this video is dedicated for both candidates, but specifically it is more relevant for international candidates. So let's get straight into the video since we are done with the introduction. So to understand equilibrium, we must understand these two definitions. So reversible reactions. Not all reactions are reversible. Excuse me, there is an aircraft going. Okay, it went. Reversible reactions. Not all reactions are reversible. They are not. Some of the reactions go to completion, but reversible reactions are reactions that do not go to completion. They take place in both directions, either in this way or in this way. From reactant to product, from product to back to reactant. So what is equilibrium? Equilibrium is a state of reversible reactions where the rate of forward reaction is equal to the rate of backward reaction. So the concentration of reactants and products stays constant. They stay constant. They do not stay equal. The concentration of reactant and product are not necessarily equal. They are different values, but they are different constant values. So no further changes occur. To graphically represent this, let me draw this line over here. So we are drawing a concentration time graph. This is for reactant, product. So the concentration of product was increasing and that of reactant was decreasing until the terrible diagram, excuse me, until they reach this state. This state right over here, where the gradients become 0 of the concentration time graph and their concentrations become constant. They are not equal. They are definitely not equal. One is over here, another is over here. They are different values, but they are different constant values. They are different values that are remaining constant. Okay. So moving on. Equilibrium law. So equilibrium law states that when a reaction reaches equilibrium, the equilibrium concentration of products, not the initial concentration of products, because initially products concentration is 0, logically speaking. So equilibrium concentration of products multiplied together and divided by, again, the equilibrium concentration of reactants also multiplied together, where the concentration of each substance is raised to a power equal to their stoichiometric coefficient. And this equals a constant value at a given temperature. This whole expression equals a constant value at a given temperature known as the equilibrium constant, or K, denoted by larger K. For rate constant, it was small k. So the value of K, equilibrium constant, is only affected by temperature. So do not get this confused in MCQs. And so we moving on. So equilibrium constant can be expressed. The expression for equilibrium constant can be written in terms of both concentration or partial pressures. So concentration means square bracket or partial pressure, and this is denoted by some kind of italic P, italic small letter P. So this is an equation we got over here, and these are the stoichiometric coefficients. I'll close the window. This aircraft thing is really annoying. Okay, so this is an equilibrium constant expression, also an equilibrium constant expression. This is in terms of concentration, C. This is in terms of partial pressure. So concentration of products, yes, product, divided by concentration of reactant, reactant, and products were multiplied, reactants were multiplied. Same thing occurring over here. But when equilibrium constant is in terms of concentration, we do square brackets. But when in terms of partial pressure, the expression we do not include square brackets. If you include square brackets, then 0 marks. Do not include square bracket here. You can include this bracket here, but P must always be in front, but not square bracket here. And these were the coefficients, and yes, they are being raised to, and the substances are, each of these substances are raised to their power of the coefficients. So one really important distinction to make here, I have talked about this most probably in the kinetics video, topic 11 video. So stoichiometric coefficients has a role in equilibrium constant expressions, but has no role, no effect on rate equations. Very important. And if you are watching this video, do refer to my first ever video on topic 11. Probably in the second video, I explained why stoichiometric coefficients have no effect on rate equations. Okay, now moving on. So equilibrium constant K and quotient Q. So this right here was the equilibrium constant. Let it be in terms of anything, concentration or partial pressure, but just the equilibrium constant here. And what is this thing? The right hand side is called the quotient, left hand side is called the equilibrium constant. So this is the quotient. So the equilibrium constant, or K, let's just say K to save time. The K only equals to quotient Q when the system is at equilibrium. So K equals to Q. This is only true at the state of equilibrium. So the Q, the quotient equals K. If the quotient equals K, what are the things we can denote? That the system is in equilibrium and there will be no further change in concentration of the reactants and products. But if the quotient Q, this side, is larger than equilibrium constant K, the system is not in equilibrium, and therefore the system will react to reduce the value of the numerator in Q. The system will react to reduce their values. Therefore, the system has to shift to this side, to the left hand side. Thus, the products will be converted back to reactants. Yes, products to reactants. Therefore, their concentration falls. This falls. Therefore, numerator decreases. So the position of equilibrium shifts to left. So opposite here, if the quotient is smaller than equilibrium constant K, the system is also not in equilibrium and will react to increase the value of the numerator. Therefore, reactants will be converted more to products. Therefore, the position of equilibrium shifts to the right. Okay, done. Okay, so now we are going to look at the rules for writing equilibrium expressions, equilibrium constant expressions. So this was an equilibrium constant expression. This part was the equilibrium constant, and this part was the quotient. So we are now learning or looking at rules for writing these expressions. So there are three main rules. So rule number 1: solids are not included in equilibrium constant expressions. You will learn, not learn more. You will just learn the fancy subtopic under which this falls, that being homogeneous and heterogeneous equilibrium. We will look at that later. But for now, and let's look at this. And these points may look quite silly, but these are all extracted from mark scheme. So this is how this is how Edexcel wants you to think of this. Think of the reasoning of this statement. So concentration of solids don't change. Yes, solid concentration does not change. It stays constant. So if it stays constant, they say, the mark scheme is saying that it is already incorporated into the equilibrium constant K. So this constant already incorporated into this constant. So therefore, no need to write or include any solid species in equilibrium constant expressions. And moreover, solids also exert no gaseous pressure. So it would also be too stupid to include any solid species in Kp expressions. Now the second rule, water, H2O, is only included in equilibrium constant expressions if it is a reactant or it is present in a gaseous state. So I'll tell you this: if water is present in gaseous state as water vapor, then it is already a reactant. Okay, so it is already a reactant. So this whole sentence could be shortened to say that H2O is only included in these expressions when it is a reactant. But if water acts as a solvent, and we look at this idea here, if water acts as a solvent, it's not included in equilibrium constant expressions because its concentration remains constant. So the whole idea is this is a beaker, water, some solutes over here. So for this solute to dissolve in this solvent, the solvent must have must be of higher quantity than the solute itself. So the concentration of the solvent must be greater than the concentration of the solute. So as water is the solvent here, the concentration of water must be greater than the concentration of the solute that is dissolved in water for it to be able to dissolve in water. So that makes quite a lot of sense. Then, so that is why we are saying if water is a solvent, then its concentration remains constant. So if any species concentration remains constant, that species, as we have seen over here, is not included in Kp or Kc expressions. Let's stick to calling them Kp and Kc to save time. So now we have to determine when is water actually a reactant and when is water a solvent. How do we identify? So we look at these two examples over here. So this is a substance, organic compound, water, organic compound in liquid state, all are in liquid state. When all substances as well as water are in liquid state, then water is a reactant. Just know that. So water is a reactant here and is included in the Kc expression. But when any one of the substances are in aqueous state, so either any product or either any reactant, or both product and both reactant are, or both are product and both are reactant are in aqueous state, but water is in liquid state. So this contrast of states. In those cases, then water is a solvent and is not taken in Kc or Kc expressions. So that is when water is a solvent, and that is when water is a reactant. Not included here. H2 is not included here. So done. Now partial pressure, the third rule. Partial pressure denoted by small p. This could have been more italicized. Italic. So partial pressure is the pressure exerted by a single gas in a mixture of gases. Okay. So gases in the atmosphere is a famous topic in GCSE chemistry. Composition of the atmospheric gases. So the pressure exerted by a single gas, let's say nitrogen, out of all of the other gases, carbon dioxide, methane, water vapor, out of all of the other gases, the pressure exerted by a single gas in that mixture is the partial pressure of the gas. So partial pressure is dependent on temperature and mole fraction, because increasing the temperature increases the partial pressure. You know that. That is physics stuff. Increasing temperature increases their kinetic energy, more collisions, more force exerted on walls or on each other. Therefore, pressure increases. Just pressure loss from physics. So don't get this confused. Equilibrium constant K only depends on temperature. But this is partial pressure. It is dependent on temperature and mole fraction as well as volume. So sum of partial pressures must be equal to the total pressure. This is quite common knowledge, common sense. Quite easy thing to grasp. And also sum of mole fractions because of fraction. So sum of mole fractions must also equal to 1. These are two statements that will help you in calculations. So will this. So if we are asked to find the partial pressure so that we can input or plug in the values in this expression and calculate P, Kp, then we definitely have to do this calculation, do this step. So this is how it's done. So the mole fraction is basically the mole of that substance divided by total mole of all other substances, including this substance. So that is the mole fraction, and if we multiply it by the total pressure, we get the partial pressure. So partial pressure is mole fraction times total pressure. Rule number 3 done. Now steps for determining Kc or Kp values. These are the steps of basically the calculations we are talking about. Don't consider these are really hard stuff. Don't just run away from the video. All we are going to look at down here is how we carry out these equilibrium equilibrium calculations. So there is a specific way of doing equilibrium or topic 13 calculations. Equilibrium calculations. So firstly, we have to write the chemical equation. Or if it's written, we have to make a table like this. This is called the ICE table. The I in I stands for initial moles, C stands for change in moles, and E stands for equilibrium moles. So the initial amounts in moles of the reactants and of the products if their initial amounts were not zero. If initial moles of reactants are not given, they are not given, you may assume them as one. No harm in assuming them as one. This is one of the calculation tricks. So I have written it in a different text color. Then the change, initial I, the amount by which the reactants and the products change, C. In reaching equilibrium, use the stoichiometry of the equation. So the stoichiometric ratio thing only comes into play when calculating this C, not in E, not in I. Okay. So lastly, the amount in moles of each substance at equilibrium. The equilibrium concentration. So equilibrium moles we have found out. If we know the volume, we calculate the equilibrium concentration. And if we know the total pressure, we then find the, from here equilibrium moles, we then find the equilibrium mole fractions and multiply by the total pressure to find the partial pressure. So below the table, write the expression for the equilibrium constant. After we have done these calculations, we will write the expression first, then we will plug in the values and find the answer and state it to the appropriate significant figure as demanded in the question. May look a lot of things, but easy, just easy instructions on how to do the calculations on equilibrium. So this is an example question. There are harder example questions, exam questions that appear in exams. So I'll go through those in other videos, specifically topic-wise videos, where I'll be doing specific questions from each topic. But that is for probably November, not November, I'll say October, not now. Once I have a big enough fan base on YouTube, if I ever do. So what example? So when 0.02 mole of sulfur trioxide, yeah, is placed in a flask of volume 1.5 dm cube and allowed to reach equilibrium at 600 degrees Celsius, 29% of it decomposes. That means 71% of it remains at equilibrium, I could say, into sulfur dioxide, yes, and oxygen. Calculate the value of the equilibrium constant Kc at 600 degrees Celsius. So this is the equation. We are already given this, or if we are not given this, we are told this data, what are the reactants, what are the products, we can find out, write out the balanced equation. But it's really important to write out the balanced equation if it's not given. Then the initial moles, yes, we are given initial moles of sulfur trioxide given, but initial moles of product, because initially there is no reaction. At time t0, there is no reaction. As time progresses, reaction occurs, products form. But initially, there must be no mole of products unless they have specified any moles of products already present. In which case, that would be a reaction that is reversible, and we would be at a stage or step in that reaction where product formation has already occurred, and we want to go from there to the equilibrium. So now the change in moles. So minus 29 because concentration of reactants or moles of reactant decreases as reaction progresses. For concentration time graph for reactants. So minus 29 by 100 into this, we get the change in moles. Okay, we get the change in mole, and change must be negative because initially must be larger. Initial moles must be larger than moles at equilibrium because moles is decreasing. Mole time graph. Moles time graph. Moles is decreasing. Therefore, the change must be negative. Because what is this change? This change is basically I hope it's understood. So change in moles we got, and change in moles for products must be positive because of this. So change in moles of products are positive. So 2 to 1:1 mole ratio of these two, therefore same value, but 2 1, therefore 2:1 mole ratio of this and this, therefore half. Okay, so this minus, we get the equilibrium mole, this plus this equilibrium mole, this plus this equilibrium mole. So as we were told, the total volume divided by the total volume, get the concentrations, plug in the concentrations. Don't forget to raise each concentration to the appropriate power of stoichiometry, and get the value of the equilibrium constant. Now, homogeneous and heterogeneous equilibria. So homogeneous reactions are reactions that involve either all gases. So basically reactants or reactants and products in which all of them are in the same phase. So if all are gases, they are indeed all in the same phase, or all solutions, e.g. all aqueous solutions, then they are forming a homogeneous equilibria. Heterogeneous reactions involve being solids reacting with gases or solutions. Solid is in a different phase or different state to gases. Solid and solution also different phase and different state. Therefore, they produce heterogeneous equilibria. Substances of same phase, homogeneous, different phase, heterogeneous. So to be able to tell whether an equilibria is homogeneous or heterogeneous, we need to look at equations like this and state symbols like this. Now the effect of changing conditions on equilibrium constant K and quotient Q. Remember, K was only affected by temperature, but Q could be affected by a lot of factors. Not much really. So changing condition, increasing the temperature. For an exothermic reaction, equilibrium shifts to left hand side. Why? We looked at the earlier video, entropy, where we read the link between S total R ln K. But things I have written over here, these are in terms of Marxim answers. So, but questions may come. They will explicitly mention to you whether to write in terms of this relationship in answers to questions like this. If you have to include or write in terms of this, you will be given that, or you will be told that instruction in questions. But this is just the general answer taken from the Marxim. So for an exothermic reaction, equilibrium shifts to LHS, left hand side, because backward reaction is endothermic, forward was exothermic. As forward is exo and backward is endo, so equilibrium shifts to left hand side or endothermic direction. So Kc Kp decreases. Why it decreases? If equilibrium shifts to this side, the concentration of reactants increases and of products decreases. Therefore, numerator decreases, denominator increases, this decreases, Kc decreases. Easy. For an exothermic reaction, I should have written endothermic. Oh, decreasing temperature. No, it's all right. So for an the effect of now decreasing temperature. For an exothermic reaction, equilibrium shifts to right hand side. As forward is exo, so it is independent of temperature, and backward is endo. It is dependent on temperature. না পড়ছিলাম স্যার খেলা কি শেষ নাকি এখন আউট কত হয়েছে তামিম খেলছে আজকে তামিমকে তোমার প্রধানমন্ত্রী ছুটি দিয়ে দিছে ঠিক আছে for an exothermic reaction, so decreasing temperature. For an exothermic reaction, equilibrium shifts to right hand side, because the forward reaction is exothermic, independent of temperature, and the backward reaction is endothermic. So backward was dependent on temperature, and we are decreasing the temperature. Therefore, backwards rate is decreasing, and forwards rate remained as it is. So and so, net effect is the equilibrium shifts to right hand side. So Kc Kp increases for the same reasons as explained here. Now increasing pressure. So 1 mole of X gas, 1 mole of Y gas, 1 mole of W gas. So increasing the pressure, equilibrium shifts to right hand side, as right hand side has fewer gas molecules. So increasing pressure favors the side with fewer gas molecules, shifts to right hand side. So quotient decreases, yes, quotient decreases as greater increase in denominator due to more moles of reactant. Now this is quite counterintuitive, because Kp was W P Px Py. This was the expression. This is the expression for Kp. So increasing the pressure, quotient decreases. Why it decreases? Because the increase in denominator, increasing pressure increases partial pressure of this equally, this equally, this equally. Partial pressure of all of these increases equally with increasing pressure. So as there were 2 here and there was 1 here, so the denominator is increasing more and the numerator is increasing less. So quotient is decreasing, but Kp is remaining constant because Kp or Kc is only affected by temperature. So the position, so Kp, if Kp remains constant and quotient is becoming smaller, then the position of equilibrium shifts to right hand side until quotient becomes equal to Kp. So by shifting to right hand side, this increases, therefore Q increases to become equal to Kp and re-establish equilibrium. Okay. Pc to the power 5 Pa into Pb. So increasing the pressure in this case, in this equilibrium over here, equilibrium shifts to left hand side. Yes, increasing pressure, equilibrium shifts to side with fewer moles of gas. Fewer moles this side, left hand side. As LHS has fewer molecules of gas, 2:5 ratio. In the mark scheme, they like to write in terms of ratio. These are all mark scheme points. So quotient increases. Why quotient increases? Increasing pressure. Increasing pressure, this P increases, this P increases, this P increases. So, but this P increases to the power of by the power of 5, and this P multiplied together, they increase by the power of 2. So the net effect of increase on the numerator is greater. They also increase, but their increase is much less. The numerator increases much more. Therefore, the quotient increases. But Kp as always remains constant. Kp remains constant, quotient becomes larger, quotient increases. Therefore, position of equilibrium must shift to left hand side. Supporting this marking point, we are saying again, position of equilibrium shift to left hand side so that this decreases and this increases. So quotient again becomes equal to Kp and re-establish equilibrium. A lot of layers behind these types of answers, but these are all mark scheme points. So this is how they want you to answer. There is no shortcut. Now increasing the concentration. Increasing concentration of oxygen decreases the value of concentration, not pressure. Increasing the concentration of oxygen decreases the value of quotient as denominator increases. Is it so? Decreases the value of quotient. 2, 3, yes. Quotient decreases. Increase in denominator is greater. Denominator increases more than numerator. Denominator increases more than numerator. Therefore, this must decrease. Position of equilibrium shifts to right until Q becomes equal to Kc again to re-establish equilibrium. But one thing I must point out is that when changing temperature, Kc changes obviously, but Kc does not change in order to re-establish equilibrium. Kc can independently become larger than Q, doesn't matter. What will happen is that Kc changes independently of Q. Kc does not have to change in a way to become equal to Q, because at a different temperature, Kc is different. Therefore, the Q for that Kc is also different. But in cases like this, where Kc or Kp are not changing, but only the Q is changing, the change in Q is such that it must become equal to Kc or Kp again. But that is not true for when changes in Kc or Kp occurs. That was not true in those cases. In those cases, the Q itself also changes. So this new Kc for a new temperature will have a new Q. New temperature, new Kc, new Q. Now the use of a catalyst. Rate of forward and backward reactions increases by the same extent. So Kc or Kp and Q unchanged. As forward and backward both increases by the same extent, therefore no changes in numerator or denominator, no changes in concentration for that matter. So Q is remaining unchanged, and Kp we can blindly say is unchanged because Kp and Kc only depends on temperature. So we can blindly say it is unchanged. So above explanation of catalyst is only true for homogeneous catalyst. If heterogeneous catalyst is used, then changing pressure has almost no effect on rate of reaction, because we did in topic 11 kinetics that rate of reaction for heterogeneous catalyst will only depend on rate of adsorption, desorption, and number of active sites available. So changing pressure has no effect, but changing concentration does have an effect on homogeneous catalyst as well as heterogeneous catalyst, because more heterogeneous catalyst, more active site, blah blah blah. But pressure is not having an effect on heterogeneous catalyst. What is the main point of this paragraph? Pressure does not have any effect on heterogeneous catalyst. Now the industrial yield and changing concentrations. This is a quite common exam question. This can appear for 4 to 6 months. So this is an exam question. In a laboratory preparation of ethanol, ethene was mixed with steam, ethene and steam to form ethanol at 150 degrees Celsius. Unit 2 level, unit 2 organic chemistry. So at equilibrium, the total pressure of the system was 50 atmospheric pressures in an exothermic reaction. The manufacture of ethanol is carried out at 230 degrees Celsius. 150, 230. We are carrying out at 230 and at a larger pressure. The overall conversion into ethanol is 95%. So increasing the temperature for an exothermic reaction must shift the position of equilibrium to this side. But still we have a yield this high. This is quite thought requiring. And increasing the pressure must shift the position of equilibrium to this side. So supports the yield. That is all right. So comment on these conditions in relation to their effect on the equilibrium. So what are the focal points? We have to comment on the effect on equilibrium, 1 point, and the overall yield of ethanol, 2 points, 6 marks. Better note. So we are back. So these are the marking points. So high temperature needed, otherwise the rate of reaction would be too slow. Higher temperatures increases the rate of reaction. Just saying that high temperature increases the rate of reaction is not enough for a 5-6 mark question. You have to also reason like this: why is high temperature needed, and why using low temperature is not enough. Why is high temperature needed, and why is low temperature not needed or not enough? Both why and that. So answer like that. So more ethanol product produced in a given time. There will be more ethanol production in a given time. Just saying more product will be produced or product yield will be greater is not enough. You have to explicitly state what is the product. So then pressure, high pressure shifts position of equilibrium to right, as fewer moles on right hand side. So high pressure favors formation of ethanol. Again, formation of product is not good enough. Formation of ethanol. So high temperature shifts position of equilibrium to left. Yes, it does shift it to left. Decreasing yield of ethanol does increase the rate of reaction, does increase the how fast, but decreases the how far. Decreasing yield of ethanol, enthalpy change of surroundings. Entropy change of surroundings becomes less positive. Yes, entropy change of surroundings does become less positive. So total entropy change becomes less positive, as total entropy change is equal to R ln K. Therefore, K decreases, and if K decreases, yield of ethanol decreases. So yield of ethanol increases, but how come we have to comment that the yield of ethanol is 95%? One possible answer is, but unconverted reactants are recycled to increase overall yield. This is a quite sneaky marking point, but it came in the October 2021 exams, if I recall correctly. So I have included it in the notes. So last point, high temperature is a compromise between overall yield and rate of formation of yield. Compromise between how far and how fast. Perfect answer. Now effect of stoichiometric coefficient on equilibrium constant / linking relationships. Stoichiometric coefficient has no effect on rate equations, but has an effect on equilibrium constant expressions. So consider the equilibrium reaction of sulfur dioxide and oxygen reacting reversibly to form sulfur trioxide. These reaction can be represented by 2 equations and hence by 2 expressions for the more than 2, actually 3 ways, and hence by 2 expressions for the equilibrium constant Kc. The values given below are at 7 to 27 degrees Celsius, 100 Kelvin. So sulfur dioxide, oxygen, 2 moles of sulfur dioxide, 1 mole of oxygen forming 2 moles of sulfur trioxide. So can be written like this. Then the Kc expression becomes like this, and value becomes like this. Can be written like this: 1 mole, half mole, 1 mole. Expression becomes like this. Value becomes different. So you see, the stoichiometric coefficient does have an effect on both expression of Kc and value of Kc. Or it can be written like this. This is the backward reaction in the backward form. Sulfur dioxide, oxygen, oxygen, sulfur trioxide, backward form. Note that Kc prime is equal to root over Kc. Yes, which was the Kc prime? Kc prime, yes. If we root over this, the 2 root over this, root over kc. If we root over kc, it becomes equal to kc prime. So root over means to the power of half. So half into 2 equals to 1. What is up with my drawing pad today? Root over means half to the power half, and half into already to the power 2 such an indices stuff means 1. So this and the three equilibrium constants are connected by the expression kc equals to kc prime whole square, or this and this. So these used to appear in section B back in the day. I have seen this question in one or two pre-2016 papers, but in this day and age, this question only appears as an MCQ. MCQ section A, last page. So distribution of a solute between two immiscible liquids. A solute distribution between two immiscible liquids. So this is just an application of what we learned so far. We learned about equilibrium constants. Not all equilibriums have to be necessarily chemical reactions. Some equilibriums can be physical processes as well. But that does not change the fact that all of these are equilibriums, and it does not change the fact that these rules, all of these things can be applied for all of these processes. So just an application. If solid iodine, yes, we are adding iodine, is added in the flask, it will get distributed between the two layers, yes, immiscible layers. So because iodine is soluble in both, why does it get distributed between the two and not remain in one? Because it is soluble in both of them. The solubility is lower than that in hexane. In hexane layer, solubility of iodine is less, and in water, solubility is more. So more of iodine, it will be concentrated. Concentration of iodine in water layer greater, concentration of iodine in hexane layer less. There is an equilibrium setup for the diffusion for the physical process of iodine between hexane and water due to being soluble in both. So this equation, not a chemical equation but a physical equation, the equilibrium constant for this equilibrium right here, application equilibrium, is called the partition constant, just a fancy name. So concentration of product, yes, numerator, concentration of reactant, denominator, perfect. No stoichiometric coefficient, 1 doesn't matter. Should have probably written like this, but you get the idea. So last topic for today, that is estimating the extent of reaction using equilibrium constant values, using equilibrium constant or K values. Therefore, we are estimating the extent of how far. The equilibrium constant for a reaction is a measure of how far a reaction proceeds to completion. However, a reversible reaction is never complete though. How far it reaches completion, but we are not saying it has reached completion. See, the value of equilibrium constant obtained is very large, then the reaction almost proceeds to completion. If it's around 1, so Kc or Kp, just a simple reaction A, B, no 1 let's give 1 for example. So if it's around 1, then the concentration of reactants and products are nearly the same at equilibrium. And if it's very small, 10 to the power 10 raised to the power of minus 10, the reaction hardly occurs. So if K is very small, that means the denominator is very large and numerator is much smaller, and denominator is the reactant and numerator is the product. Therefore, the reactant concentration must be much 10 times larger than the product concentration. Concentration of B must be 10 times larger than concentration of A. Concentration of product must be 10 times larger than concentration of reactant. So if there is 10 times more reactant than product, then the reaction hardly occurs, producing very small quantities of products at equilibrium. So this concludes topic 13, equilibrium. And make sure to share this video, subscribe for more content like this. And in the next video, will be on topic 14, acid-base equilibrium. That is a very lengthy topic, I would say. Lot of things to talk about there. The kinetics note was 11 pages, and entropy and energetics note combined was only 8 pages, and this is only 6 pages with lots of gap. But the acid-base equilibrium note is 9 pages, 8 to 9 pages. So that's it for this video, and see ya.